Hell no! As soon as I caught Dave, I knew they'd stop.
This is a picture of Lance Armstrong. He was an American cyclist who, in 2005, when this picture was taken, had just won his 7th consecutive Tour de France title. It was an amazing feat, but ultimately he would have been struck of all of those accolades and been accused and later convicted of doping, injecting performance-enhancing drugs to ultimately help him beat all of his rivals. But it wasn't until 2012 when Armstrong was ultimately stripped of his awards. So how do we catch cheats like Lance and others using chemistry? How can we prove beyond a shadow of a doubt that their abilities are unnatural? Well, it turns out that the answer lies in isotopes. Alright, so from last class we talked about isotopes. And now I want to go into that topic in just a little bit more detail. We defined isotopes as different versions of a chemical element who really differed in terms of the numbers of neutrons, right? So we were playing with these, we were building new atoms. The one I've got here is what we would have called carbon-12, right? So the mass number, when we say carbon-12, we use the mass number, which is the sum of protons and neutrons, right? So there's 6 of each. That's why we get carbon-12. And it just so happens that carbon-12 is stable. In fact, we use it to base the atomic mass unit system on. But we can add more neutrons to that, and sometimes this is still stable. And for carbon, adding an extra neutron is stable. We've got carbon-13. And so these are what we call isotopes. They are the set of elements having the same number of protons but different numbers of neutrons. Now, of course, electrons can come and go, and they will become ionic or not, based on how many electrons you have. It might be a neutral atom, but isotopes are the set that differ based on the number of neutrons. So a fundamental question when thinking about that, and this is something I would encourage you to always think about, is how do we know that? Again, remember how small these atoms are. They're impossibly small. Remember experiments like Rutherford's experiment and Millikan's experiment trying to measure charges on electrons. How could we possibly tell the difference between these different elements when in fact they behave chemically very, very similarly? Okay, so we reviewed last class that charge has almost everything to do with the chemistry. What am I drawn to? What am I repelled from? Who do I make bonds with? That is almost entirely governed by charge. So how is it that we're going to tell the difference between different isotopes and even know that they exist? That's a tricky question, unless you have something called a mass spectrometer. So this is a schematic of a mass spectrometer, probably overly simplistic, but nonetheless it'll get the job done for us today. In an experiment like a mass spectrometry experiment, what you start by doing is taking your sample and you vaporize it. Now that can be done with just a lot of heat, right? You can vaporize most chemical samples. And then you pass it through this chamber where it's bombarded with electrons, and the purpose of that is to give it a charge, an electronic charge. And then you pass it through these plates, which is really just meant to fire those elements as quickly as you can around this turn. Okay, so that's key. You're forcing these elements to take a turn. Now in this schematic, we're talking about neon specifically. So imagine we've got billions and billions of neon atoms inside this chamber, and then we fire them through this gun and make them go around a corner. How do we make them go around a corner? We simply make them pass through a magnetic field. Okay, so remember, these things will be deflected by a magnetic field. They're charged. And so as they get deflected by the magnetic field, they travel down this chamber and will ultimately collide with a detector. But here's the thing. They will collide in different places along this chamber relative to their mass. Okay, so if you have an isotope that has more neutrons, then it's going to be heavier. If you have an isotope that has less neutrons, it's going to be lighter. So take a look at the three we've got here. We've got neon 20, which would be the lightest of the three, neon 21, which would be in the middle, and neon 22, which would be the heaviest of the three. And perhaps not surprisingly, you notice that as those elements try to take the corner, the light one takes the corner too quickly. The heavy one can't quite turn enough, it's too massive, and it collides into this side. In other words, it doesn't turn quickly enough. And the Goldilocks element, neon 21, makes it through perfectly and collides with the detector. So imagine you're watching your detector and you're counting the number of collisions that happen down here, and you've got your sample of neon with billions of atoms coming through. You would notice that you see an awful lot of collisions if these magnets are tuned to see neon 21. So what do you need to do? Well, you need to change the strength of this magnet to make it, say, weaker. And if you make this magnet weaker, then you will cause neon 21 and neon 22 both now to be too heavy, and you can instead go looking for neon 20. So in other words, don't apply as much force. The neon 20 will now not be deflected as much, and the neon 20 will make it to the detector while the other two crash into the side. And then vice versa, if we wanted to go looking for neon 22, we dial up the strength of the magnet if we're looking for heavy particles, because we really need to force them to make that corner. But when we do dial up that strength, we will necessarily cause neon 21 and neon 20 to both collide into the side, and we'll only be looking for neon 22. So if we continue this experiment over a long period of time with many, many different magnet strengths, the result is what we call a mass spectrum, which is shown over here on the right. And what this is showing us is relative abundance. In other words, how many collisions do we count as a percentage of the total for neon 20, right? And we know that we would be looking for that one based on the strength of our magnet, neon 21, and neon 22. Notice that if we had run this experiment, we would have seen an awful lot more collisions. It would have been much more frequent process to see collisions had we dialed down the strength of this magnet so that neon 20 could come through. Consequently, when we go looking for neon 21 and 22, we see comparatively far fewer collisions. This is the evidence that we collect to tell us about how much of each of these isotopes there are. Not only do we discover that there are actually 3 flavors of neon out there with 3 different numbers of neutrons, but we also discover how abundant each one of them are. The vast majority seem to be neon 20. And if we worked out the percentages, we would find that about 90.5% of all neon is neon 20. 0.27% of all neon is neon 21, and about 9.25, or the rest, is neon 22. We discover this from exactly this sort of experiment. Right? Now, relative abundance is a very important term because if we go back to the periodic table that we started to look at last class and we go looking at neon, we discover that neon, element number 10, therefore it has 10 protons, has an atomic mass of 20.180. Now, what should be obvious is that that isn't 20, 21, or 22. It's neither of them. It is an amalgamation of those 3. And in fact, where this number comes from, where this atomic mass of each individual element, it comes from an average of those isotopes that are abundant in nature. But it's not just an average of 20, 21, and 22, because of course the average of those 3 numbers would just be 21. It's a weighted average. In other words, you take 90%, or to be more specific, 90.48% of neon 20, or the mass of neon 20. And then you take 0.27% of the mass of neon 21. And then you take 9.25% of the mass of neon 22. Average those, and that's what goes in to create the mass that you see on the periodic table. So let's take a look at that in just a bit more detail. Now that we know the relative abundances of each isotope of neon, how are we going to come up with the weighted average to go onto the periodic table? Well, in my mass spectrometry experiment, not only would I be able to measure the relative abundance of each of the isotopes, but I'd also be able to measure their mass very, very accurately, assuming I have a sensitive enough magnet. Now the mass of neon 20 is 19.9924 atomic mass units, and its relative abundance is 90.48%. So if I represent that percentage as a fraction, i.e. 0.9048, I can write it like this, and then add the rest of my isotopes. Neon 21, for example, is a little heavier. It weighs 20.9938 atomic mass units, and its abundance is only 0.27%. In other words, not very abundant at all. And the final isotope is neon 22. That weighs exactly 21.9914 atomic mass units, and its abundance is 0.0925. Putting all of this information together gives us that 20.18 number that we see here on the periodic table. So that's where these atomic masses come from. They come from a weighted average of the natural abundance of isotopes that we have here on planet Earth. And that's why none of these atomic numbers correspond exactly to any particular mass at all. Interestingly, there isn't an element of neon anywhere in the universe that actually weighs 20.18 atomic mass units. This is just an average. But that's useful because when we use neon in the lab and we take a sample of neon, that sample will have within it a natural abundance of neon. And so using this mass allows us to calculate properties of that sample, like numbers of moles, for example, very accurately. All right, so we know that we have this thing called a natural abundance. If we go looking for different isotopes, we see the prevalence of certain isotopes more than we see the prevalence of others. What is it that governs that? It's a little bit complicated, but essentially, as I said before, what tends to work well, at least for the lighter atoms in the periodic table, is a number of neutrons, or n, as shown in this diagram, equal to the number of protons, or Z, as shown in this diagram. So if you go through plotting number of protons on the horizontal axis and number of neutrons on the vertical axis, and then ask yourself how long do the isotopes of these various combinations last, you get the image that you see here. So what we're doing here is we're measuring the half-life, which is really just a measure of how long will it take before half of this sample spontaneously decays. Now, if your element is stable, or if your specific isotope is stable, it'll be indicated in black on this diagram, and otherwise it'll be color-coded. So for example, these blue dots here correspond to certain combinations of protons and neutrons that don't happen to be very stable, since they'll probably spontaneously decay in about a second. However, these ones along the middle here that are shown in black are the more stable combinations of each of the proton-neutron combinations. Now, as you look at the lower number, so the lighter elements, generally speaking, the most stable combination is that when Z is equal to N, the same number of neutrons and protons. And indeed, we saw this when playing with our models here. As we throw the numbers of neutrons out of whack, all of a sudden these elements don't tend to be as stable anymore. And as we throw it even farther out of whack, that isn't helping anything. So as I bring the number of neutrons down more close to what they would be equal, we get elements that are more stable. So isotopes that we can actually interact with in the lab tend to have similar numbers of protons and neutrons. Now there's a bit of flexibility that's indicated by how broad this distribution is. You can make isotopes of all different types, but generally speaking, you don't get too far away from the number of protons as you're adding neutrons. So some other key takeaways that we can glean from this image, just some general information about isotopes. Generally speaking, isotopes with an atomic number of greater than 82, so more than 82 protons in the nucleus, they're just really not stable elements anyway. So these come as the greatest proportion of the radioactive elements that we deal with. And this shouldn't be a huge surprise to you, since, let's not forget, what we're trying to do is cram 82 positively charged particles into virtually the same position in space. That's a really difficult thing to do. It shouldn't make a lot of sense about how we even cram a few of them in, let alone 82. So as you get bigger and bigger, more and more protons, you get less and less likely to find any stable isotope at all. And past 82, they're just unstable, generally speaking. Of the elements that are having atomic number less than 82, all have at least one stable isotope, except for technetium, which is Z equals 43, so 43 protons, and promethium, so that's Z equals 61. They don't have any stable isotopes. And this interesting fact gives us a bit of a hint as to what makes a stable nucleus. Notice that those atomic numbers are odd, 43, 61. Interesting. Isotopes with atomic number less than or equal to 20 show a strong tendency to favor combinations where the neutrons and protons are equal, like I said before. Common examples are carbon-12, nitrogen-14, oxygen-16. And now back to those odd numbers of nucleons I just mentioned. It turns out that if you keep track of the number of stable isotopes you find and tally them by how many protons and neutrons they have, you discover that even numbers of each are particularly likely to be stable. In fact, about 60% of the Earth's stable isotopes are ones who have even numbers of both protons and neutrons. All right, so how are we going to use all this information to catch the cheaters, to catch those who choose to dope in sports? Well, it actually has an awful lot to do with isotopes. It turns out that naturally occurring carbon, things like plants and animals and us, tend to maintain a very stable ratio of carbon-13 to carbon-12. Synthetic testosterone, however, or other anabolic steroids, tend to not have as consistent a ratio of carbon-13 to carbon-12. So those who tend to use synthetic testosterone or other anabolic steroids will have that unique signature within their blood or urine that shows that they have a different ratio of carbon-12 to carbon-13 than what would otherwise be expected in a living system. A mass spectrometer, as discussed today, is a key tool to identify these anomalous ratios of carbon-13 to carbon-12 in athletes and help prove irrefutably whether or not they've been doping.